Welcome to Civil Engineering Edge. In today's video, we're breaking down everything about reinforced concrete retaining walls, what they are, types, design methodology, is code guidelines, where they're used, and their many benefits. Whether you're a student or a professional, this is your complete guide. Segment 1. Description of retaining walls and their types. Retaining walls are rigid structural elements designed to retain soil or any other granular material on one side, allowing a vertical or near-vertical change in ground elevation. They are essential in providing lateral support to vertical slopes of soil that would otherwise collapse into a more natural shape. These walls resist the lateral pressure of soil, water, or any other load behind them and are critical for structures built on sloped or uneven terrain. Reinforced concrete retaining walls are popular due to their strength, durability, and versatility. They combine concrete with steel reinforcement, enabling the structure to resist significant lateral loads while remaining slender and economical. Let's look at the main types of retaining walls. 1. Gravity retaining wall. These rely purely on their own weight to resist earth pressure. Made of concrete or stone masonry, they are typically thick and suitable for small height applications. 2. Cantilever retaining wall, the most commonly used type. It consists of a vertical stem and a base slab toe and heel. Reinforcement helps resist the bending moments and shear forces, suitable for heights up to 6 to 7 meters. 3. Counterfeit retaining wall, similar to cantilever walls, but includes diagonal supports or counterfeits connecting the stem and base slab, which reduce bending moments. Ideal for walls above 7 meters. 4. Buttressed retaining wall, a reverse of the counterfeit wall. The supports buttresses are placed on the front face, used where space behind the wall is restricted. 5. Anchored retaining wall. This type uses anchors or tiebacks to provide additional stability suitable for high loads and limited space scenarios. Each type is selected based on site conditions, soil pressure, height, and economy. Segment 2. Method of design step-by-step. Designing a reinforced concrete retaining wall is a multi-step process that integrates principles of geotechnical and structural engineering. Here's a step-by-step guide to designing a typical cantilever retaining wall. 1. Gather design inputs. Wall height h. Backfill type and slope. Surcharge loads, for example, vehicles, foot traffic. Soil properties. Unit weight gamma, angle of repose A, bearing capacity, water table depth if applicable. 2. Determine earth pressure. Use Rankine's or Cowlam's earth pressure theory to calculate the lateral earth pressure based on soil type and slope. Account for surcharge and water pressure if present. 3. Propose wall dimensions. Stem thickness typically tapers from bottom to top. Base slab width, approximately 0.6 times. H. Heel rear part of base, 0.45 to 0.55 times. H. Toe front part, 0.3 to 0.35 H. 4. Stability analysis. Overturning check. Ensure resisting moment due to self-weight is greater than or equal to 1.5 times. Overturning moment. Sliding check. Friction and passive resistance must counteract lateral thrust. Fs is greater than or equal to 1.5. Bearing pressure check. Maximum pressure should be less than allowable soil pressure. Use trapezoidal stress distribution. 5. Design reinforcement. Stem acts as a vertical cantilever, reinforced accordingly. Heel and toe slabs act as horizontal cantilevers and must be checked for bending. Use bending moment and shear force formulas M equals WL, 2, V equals WL. Apply proper anchorage and development length. 6. Check for serviceability, limit crack widths and deflection. Ensure exposure-based concrete cover per is 456 to 2000. 7. Drainage provision. Provide weep holes at regular intervals. Add filter material behind wall to prevent clogging. 8. Detailing and drawing. Prepare structural drawings showing dimensions, reinforcement layout, bar bending schedule, and all section views. Accurate design ensures structural safety, cost-effectiveness, and longevity. Segment 3 is recommendations on stability of retaining walls. The Indian Standard Code is 456 to 2000 and is 3370 provide comprehensive guidelines for the structural design and safety of retaining walls. These include 1. Factor of safety against overturning. The wall must resist the tendency to rotate due to lateral earth pressure. IS Code recommends a minimum factor of safety of 1.5 against overturning. 2. Factor of safety against sliding. The wall must resist horizontal movement. A minimum safety factor of 1.5 is required without considering passive resistance. With passive resistance, a minimum of 1.3 may be used. 3. Bearing pressure on soil. The maximum pressure exerted on soil below the wall must be less than the soil's safe bearing capacity (SBC). Pressure distribution is assumed trapezoidal or triangular depending on eccentricity. 4. Drainage measures. Weep holes or drainage pipes are mandatory to prevent buildup of hydrostatic pressure, which can drastically increase lateral loads. 5. Reinforcement detailing. As per is 456, minimum reinforcement in walls must be 0.1% HYSD and 0.15% mild steel of cross-sectional area. These recommendations ensure safety, serviceability, and durability of the retaining wall over its design life. Segment 4. Where are the best uses of retaining walls? Retaining walls are versatile and essential components in many civil engineering and architectural projects. Here are some of the best applications of reinforced concrete retaining walls. 1. Highway and road construction. On hilly or uneven terrain, retaining walls support the roadway by holding back cut soil and preventing landslides. They also stabilize slopes along highways and flyovers. 2. Basement and underground structures. In urban construction, basements often require retaining walls to hold soil back while also resisting hydrostatic pressure from groundwater. 3. Bridge approaches and railway embankments. Retaining walls offer structural stability for earth embankments at bridge ends and along railway lines, especially in sloped areas. 4. Land development and landscaping. In real estate and architectural landscaping, these walls help level land, create terraces, and form aesthetic boundaries in gardens, parks, and buildings. 5. Waterfront and marine structures. Used in ports, canals, and dockyards to resist earth and water pressure. These must also handle wave and current actions. 6. Industrial and infrastructure projects. Power plants, storage yards, and industrial facilities use retaining walls for bulk material storage and to retain earth near heavy foundations. Each application benefits from the wall's ability to provide support, resist erosion, and maximize usable land area, especially in space-constrained or sloped sites. Segment 5, Benefits and Conclusion. Reinforced concrete retaining walls offer numerous benefits in structural and geotechnical engineering. High strength and stability, capable of resisting heavy lateral earth pressures. Durability, properly constructed RCC walls last for decades with minimal maintenance. Space utilization, maximizes usable land area in sloped or restricted sites. Versatility, suitable for varied soil conditions and structural demands. Aesthetic options, can be faced with stone, tiles, or textured concrete for enhanced visual appeal. Environmental protection, controls erosion, manages drainage, and prevents landslides. Reinforced concrete retaining walls are vital for ensuring the safety and stability of earth structures across infrastructure, urban development, and landscaping. Their successful implementation requires a sound understanding of soil behavior, structural mechanics, and code-based design practices. When designed and constructed correctly, these walls not only perform their function effectively, but also add long-term value to a project. Thanks for watching this detailed guide on reinforced concrete retaining walls. If you found it helpful, give us a like, subscribe, and share it with your fellow engineers. Have questions or need examples? Drop them in the comments. This is Civil Engineering Edge, where learning meets engineering.